You know, building a machine learning model from scratch can feel, well, super complicated, right? But it really doesn't have to be. Today, we're going to pull back the curtain on the whole process using Python's awesome Scikit-learn library. Let's jump right in. So, does the whole idea of building an ML model seem a little intimidating? Like you've got to be some kind of math whiz or a coding genius just to get your foot in the door? That's a totally common feeling, but I've got some really good news for you. The thing is, Scikit-learn has what its creators call a really clean, uniform, and streamlined API. But what that really means for you and me is that once you learn the basic pattern for one model, you pretty much know the pattern for all of them. It's fantastic. And that right there is the core idea of what we're talking about today. There's this universal blueprint, kind of a secret recipe for using almost any machine learning algorithm in Scikit-learn. And trust me, once you see it, you can't unsee it. Okay, so here it is, the 5-step pattern. It's actually really simple. 1, you choose a model. 2, you pick its settings. We call those hyperparameters. 3, you get your data ready, splitting it into features and a target. 4, you fit the model, which is just a fancy word for training it. And finally, step 5, you use that trained model to predict stuff. That's it, seriously. This is the blueprint for pretty much everything. So to really see this pattern in action, we need an example, right? Let's use one of the simplest yet surprisingly powerful classifiers out there, the Naive Bayes Classifier. So what is a Naive Bayes Classifier? Well, in a nutshell, it's a model that just uses probability to classify things. But here's the cool part, it's incredibly fast and simple. It's so straightforward that it's often the very first model you should try on a problem, just to get a baseline for how well you can do. All right, theory is great, but let's get our hands dirty and look at some code. We're going to walk through our 5-step pattern using a specific type of Naive Bayes called Gaussian Naive Bayes. Let's see what it looks like. Okay, so right off the bat, we're knocking out steps 1 and 2. We just import the Gaussian NB model from the Scikit-learn library, and then we create an instance of it. Look how clean that is, just 2 lines of code. So what's really happening here? That first line, that's us choosing our model class. That's step 1. The second line, we're creating the actual model object. And here's a little bonus with Gaussian Naive Bayes. Step 2, choosing those hyperparameters, is already done for us. It's so simple, it doesn't have any that we need to fiddle with. How great is that? All right, next up, step 3, getting our data in order. Think of it this way. Before a model can learn anything, we need to give it a textbook to study from and a final exam to test it on. That's exactly what this train test split function does. This really gets at a core idea in machine learning. We split our data into 2 key parts. The predictors, you can think of these as the clues or features the model will learn from, and the target, which is the answer we want it to predict. We let it study on the training set, and then we test its knowledge on data it's never ever seen before. And here it is. This one single line of code is where all the magic happens. Step 4, fitting the model. This is the moment it actually learns. So when we call that .fit method, we're basically telling our model, hey, look at this training data and figure out the relationship between the predictors and the target. It crunches the numbers, analyzes the patterns, calculates all the probabilities, and stores everything it learns inside that model object. The result? A fully trained model, ready for that final step. And finally, we get to step 5, the payoff. We take our newly trained model and we ask it to make predictions on that test data we've been keeping aside. So the predict method takes those unseen features our predictors test and uses that internal logic it learned during the fit step to guess the outcome for every single one. What you get back is a new array just filled with the model's best guesses. So if you zoom out a little, the whole process really just boils down to these core functions. You fit it to train it, you predict it to use it, and you can even score it to see how well it did. And the beautiful thing is, this consistency is there across dozens of different models. That's what makes Scikit-learn so powerful and honestly, so easy to get started with. Okay, so we've seen how to build the model, which is great, but let's take just a second to talk about why it works. What's the secret sauce inside Naive Bayes? Deep down, this classifier is built on a really famous formula called Bayes' rule. Now, don't worry, you don't need to memorize the math here. Just get the concept. It's basically a formal way of updating your beliefs based on new evidence. It's what allows the model to learn from the data we give it. So where does that naive part come from? Well, it comes from a really big and frankly often wrong assumption. The model is naive because it assumes every single feature is completely independent of all the others. It's like assuming the outside temperature has absolutely no relationship to whether it's sunny or cloudy. Now, this crazy simplification is exactly what makes the model so blazingly fast.
Okay, so you've seen the code, you've seen the concept, and the most powerful part is realizing what this now unlocks for you.
This is the big takeaway, right here. You now know the universal pattern. So what if you want to try a way more complex model, like a random forest or a support vector machine? Guess what? You just swap out the model class back in step 1. The rest of the pattern, arranging data, fitting, predicting, it stays exactly the same. With this one blueprint, you've literally just unlocked dozens of algorithms.
But let's end with a fascinating question to chew on. We know that the core naive assumption that all the features are independent is almost never actually true in the real world. So why on earth does this super simple model work so surprisingly well on really complex problems like spam filtering? It's a great little puzzle to think about. Thanks so much for tuning in.